Hello, I am Rui Cardoso, Senior Lecturer for Aerospace Engineering. This face you are seeing there is my face, and I'm going to introduce you to statics. So I'm going to show you some sample lectures and tutorials on statics. So if you want, for some reason, to email me with any query, you have my email address here. You also have these Instagram, Snapchat, Facebook, Twitter, things for Brunel, which you can try to follow. So what I'm going to cover in these sample lectures and tutorials is basically material for your year 1 at Brunel. So I'm going to cover statics only. Of course, you are going to do many other things, but the main topics I would like you to focus is basically the first three: vector analysis. I'm going to give a very quick review of vector analysis with the basics. And then I'm going to move to equilibrium of a particle, where a lot of vector analysis is required. Then I will introduce moment produced by a force vector. So these are quite basic but extremely important concepts that you need to know very well for the remaining of your lectures. Then I will move to the equivalent system force moment, where you will learn how to basically build an equivalent system that is in the same equilibrium conditions as the original system. That will be very important for the topic that follows, which is equilibrium of rigid bodies, which is the main topic in statics. We will study many different types of supports. The bodies or the rigid bodies, they need to have supports. They cannot be levitating in the air. And then we are going to learn how to replace those supports with forces, which are called reactions. And we are going to learn how to derive the equilibrium equations. Basically, these equilibrium equations will make sure that your body is in equilibrium. And then from those equilibrium equations, you can calculate many different unknowns. Then we will talk a little bit about beams. We will derive the transverse shear force and bending moment diagrams for beams. So this is a kind of introductory video I will have for all these sample lectures. Of course, different lectures will have this same introductory video, but they will refer to different topics on this table of contents if you want. Another thing you can, if you are more curious, I have a YouTube channel which you can, if you are interested of course and curious, you can try to see what I have there. So I have a lot of lectures in that YouTube channel, so you can search for that channel by googling Rui Cardoso YouTube. I have lectures for more advanced years, so I recommend at this point you not to see those lectures. But I also have some supporting material for statics in year 1 there in the YouTube channel. So I think is a nice thing for you to see as well. I would like also to say that all the examples I will be doing in these lectures and tutorials, not all of them, but many of them were taken from these recommended books I have listed here in this slide. So Engineering Mechanics Statics from Ibler, or from Vector Mechanics for Engineers, Statics from Beer and Johnson, from Engineering Mechanics Statics from Marian, Bolton and Craig, and also from my own book, Stress Analysis for Lightweight Structures, a MATLAB-oriented approach. So all the examples you will see in the videos, sometimes I refer which book I've taken the example, sometimes I don't, but these are the books that I follow. So in case I forget to mention which book I took the example, you have here the list of books, so you know where they came from. Right, thank you. So we will move now to the specific lecture. Let's start. So as I said, this was question 1 in last year exam in May. In fact, it was this May. So basically what you have in this example is you have a beam, AB, and you have a strut, this strut CD, okay? So the beam AB is hinged at point A, so this point A, this support is an hinge, so it will allow rotation about this point. The strut CD is hinged at point D, at support D, and it is also hinged at point C with the beam. All right? So all rotations are possible here. So this is a two-dimensional problem. It's in 2 dimensions. Rotations are possible, so it means you will not have moments as reactions. Right? And then you have this 8 kilonewtons applied at point B. And what I wanted you to calculate in this example was well, I didn't put the questions here, but it was the reactions at the supports, support A and support D. And I wanted you also to calculate the force in the strut CD. Okay? That was the questions. And before we start solving this example, I will have to introduce or discuss with you a bit more about this strut here. Because the reason why I want to discuss this strut with you first is because if I don't do that, what you tend to do is when you build the free body diagram, you are going to say, okay, we are going to have a horizontal reaction here and here that I will call AX and AY, which is correct, and I'm going to have a vertical and horizontal reaction here that I will call dy dx, which is also correct, is not wrong. But the problem is you will then get stuck here because why? You will have 4 unknowns for reactions, and in a 2D problem we have only 3 equilibrium equations. So we don't have enough equilibrium equations. So if we solve this way, we cannot solve this problem. And that's why I need to talk with you, before we continue, that's why I need to talk with you about this strut CD. And in order to do that, I'm going to start with a very simple strut, like this. So let's say this is point A, point B. Let's say, for example, the length of this strut is L. Okay? Let's imagine that I will have a coordinate system here. Let's say this is my X direction, this is my Y direction. And so basically what I'm doing is I'm building the free body diagram of this strut. So I need to include now the reactions. Which reactions am I going to have? Well, I'm going to have here By, Bx. Agree with me? So don't forget, the strut is hinged at point A and point B. So same thing at point A, I will have Ax and Ay. You all agree with me? These are the reactions I have in a strut. And what I'm going to do now is I'm going to write the equilibrium equation for the moments. So what I'm going to do is I'm going to calculate the moments produced by these reactions about point A. And I'm going to do it, all these moments in a two-dimensional problem, I will only have a component in Z direction, agree, for the moment. Component in Y and X direction are going to be 0. So this moment I'm going to calculate now is the Z component of the moment vector. And if I start with point A, these two reactions at point A, they don't produce any moment about point A. You agree with me? Yeah. So I don't need to calculate the moment produced by these two. So I need to focus only on these two reactions at point B. They will produce moment about point A. Not all of them. For example, if you look at Bx, if you extend this force Bx, if you extend this force Bx, you can see that this force will pass through point A. So it means my distance in the perpendicular direction is going to be 0. So it means this force Bx does not produce moment about point A. You agree with me? You agree with me or not? Bx does not produce any moment about point A. So in fact, the only reaction that produces moment about point A is By. You agree? And that moment is what? So we need to have this distance in the perpendicular direction, which is equal to L, right? So that moment is going to be L times, so L is my distance in the perpendicular direction to By, and I need to multiply now this with the force, which is By. You all agree with me? And this is all the moments we have in this strut. This is all the moments we have at point A. We don't have anything else. And in order for this to be in equilibrium, this moment needs to be equal to what? To 0, right? Now, if you look carefully at this equation, what we have here is Lby equal to 0. So it means L is equal to 0 or By is equal to 0. You agree with me? Let's look at first one. L equal to 0. Do you think this is possible? L equal to 0 means no strut, right? So this is not possible, right? So, in order for this strut to be in equilibrium, what needs to happen here? By equal to 0. So this means what? There is no reaction for a strut in these conditions. Only for a strut in these conditions, we cannot have a By reaction, a reaction in the perpendicular direction to the strut. Right? You all understand why, right? I show you here why. If I do the same analysis, now calculating the moment about point B and B, and saying that moment equal to 0 to be in equilibrium, just a moment. If I do that, my conclusion will be Ay, so we will arrive at L times Ay equal to 0. So this means I will need to have Ay equal to 0 as well. That will mean no reaction also in the vertical direction in my strut. So, conclusion is, if I have a strut that is hinged at these 2 points A and B, the only reactions I can have are forces in the axial direction of the strut. AX and BX. And these reactions, AX and BX, they are going to be equal to the force in the strut. Okay? So why is this important for our problem? Because if we go back to this example, we have our strut CD here, right? When I built my free body diagram for this structure, I can say at point A, I will have AY, AX. Of course, I need to have this. But here, at point D, what I'm going to have is, I'm going to have a force, which is going to be the force in my strut. And the good news is that I know the direction of this force. This force needs to have the direction of my strut, right? I know the direction of the strut. I have dimensions here. I can calculate the angle very easily. So in fact, because I know this for the strut, I will only have one unknown at point D and not two. So if you count the number of unknowns now, you will have three unknowns: AX, AY, FCD, which is the force in the strut. And now you can solve this problem very, very easily, right? Yeah.
At C, is it a support or not?
C is a support. C is an hinge as well, yes. You have an hinge at point C and you have an hinge at point D. That's why I represented this strut with an hinge. Imagine this is your point D. This is your point C from your strut, right? When you have an hinge, you have these two reactions, but we concluded here that the vertical reactions, they need to be zero. The vertical or the reactions in the perpendicular direction to the strut, they need to be zero, right? So that's exactly what I'm doing here. I'm saying here that this reaction in the perpendicular direction of the strut, this reaction cannot exist. Because of this here. I show it here, right?
So, if there was a hinge at C, at B, would there be no AY as well?
There is an hinge at D.
But if there was a hinge at B,
At B.
Then there would be no AY?
A B.
Yeah, if there was a hinge there.
But you don't have any support
If you
here.
added a hinge there.
Or if you had like something like this, imagine you have. Well, if you have an hinge here, of course, you will then add to replace this hinge with these reactions, right? But then this is not a statically determined structure. You cannot solve like these methods we are doing equilibrium equations. You need to use energy methods. Is a different story. Okay, but you don't have this hinge here. Okay. Yes.
What about the weight of the strut itself?
We are neglecting the weight. It is not because the question of the exam, you have more wording below. I just didn't include here, but it is said there. Neglect the weight of the
What made you choose the direction of FCD as downwards?
Okay, the question is, why did I choose the direction of FCD downwards and not upwards? Well, like you saw today in the morning, we don't know the initial orientation of the reactions, right? So we assume this initial orientation. Then, after getting the equilibrium equations, if you get a negative value, it means your initial guess was wrong, and then you need to change that direction. But we are going to do it now.
Say, you worked it out and it was negative.
Yeah.
You realised it was in the wrong direction. Is it still sufficient to give a negative answer because the diagram doesn't really matter?
Well,
if you just change the direction.
Okay, imagine you get, for example, at the end, after solving equilibrium equation, you get this, minus 100 newtons, right? You get this result for your force in the strut. And this was your initial configuration, for your initial assumption for the force FCD. So what you have to do is then you need to reverse this FCD. So your real force on the strut needs to be in this direction. and this is going to be equal to 100 Newton. So it means your strut will be in compression in that case. I don't know if that was your question.
I mean, it kind of was. But the thing is, because the numerical answer, is it still okay for it to be negative or positive?
Yeah.
Okay, but it's just depending on your configuration.
Yeah.
You have to redraw the diagram here.
Sorry?
It's minus 110.
Yeah.
So you have to redraw the diagram.
No, we still have to write the equilibrium equations and solve this problem for the reaction, right?
You have to redraw the diagram.
Oh, you have to redraw. Oh, I mean, in your exam. Now, I will be happy with this. Okay? Because if you arrive at this point, it means you calculated the resultant of the forces, you evaluated the moments, you wrote the equilibrium equations, right? You did everything, right? But this is what it means. When you get a negative value for a reaction, it means your initial guess for the direction of the reaction was wrong. Then you need to go back and reverse. But we are going to do now this example. Okay?
There will be no reaction at C.
Well, depends on the free body diagram we are going to do, okay? So we are going to... Let's solve this, because if we start solving this, many of these answers are going to be... Many of these questions are going to be answered, all right? So let's do the free body diagram first. So we have to do something like this. This is my beam. And I have my strut here, right? So I decided this is my free body diagram. Okay? So I isolated this, the beam and the strut, they are still linked. But in order to get this free body diagram, I have to remove the support. So I removed the support at point A, which is this point here. So this is my point A, right? So I removed the support here. So I removed the support. I removed this link or this connection there. So it means I need to include here my reactions at point A, which are AY and AX. Okay? In order to isolate this structure, I also had to cut this support or remove this support at point D. And then if I remove the support, I need to replace the support with the reactions. But you know you have a strut here, and you know that the only reactions you can have in this strut is a force in the axial direction of the strut. So I'm going to include that force here, and I'm going to call it FCD, which is the force in my strut. And I know this direction. If you want, I can write something like this. I know this angle, right? How much is this angle? 45 degrees. So I know that this force FCD, it needs to have the direction of the strut, because otherwise this strut will not be in equilibrium. We made that conclusion here in the analysis of this strut. So these are all, yes?
I think it's 45 degrees.
Why is 45 degrees? So this angle is same as this, right? You agree with me? Because so if you call this alpha, the tangent of alpha is equal to 1, right? Is 1.5 over 1.5, and then alpha needs to be equal to 45 degrees, right? Okay, you might now be saying, I'm quite sure many of you are wondering, what about point C? What about this point C? This hinge at point C? Why don't I put the reactions at point C? My question is, did I separate the strut from the beam at point C? Or my free body diagram includes the strut and the beam connected or linked at point C? I didn't break up the connection at point C, right? So I don't have to put the reactions there. They are internal forces in that case. Only when I cut or break up the connections, I need to put the reactions. If I cut a cable, I need to put the force in the cable. If I remove a support to isolate my structure, I need to put the reactions at that support, right? In this case, I didn't remove the strut from the beam at point C. I didn't do that. So I don't put reactions there. This is quite critical. I can tell you last year, some of your colleagues, they decided to put, many of them, decided to put reactions at point C, and then, of course, they got completely stuck. All right? So that's why the free body diagram is extremely important. If you don't do it correctly, you will get more unknowns than equations, and then you cannot do it. So what do I need to represent now? Well, I need to add the external force of 8 kilonewtons. That I need to add, of course. And the last thing I have to do is just to include a coordinate system. So let's say this is my x-axis and this is my y-axis. Okay? And this is my free body diagram. Now I just need to, again, build the equivalent system, force, moment. Let's do our equivalent system at point C. Okay? I want you to calculate the resultant of the forces at the resultant of the forces, and I want you to calculate the moments at point C. You can choose any point. I decided to choose point C. Why? Because if I choose point C, the moment produced by FCD about point C is 0. I don't need to calculate. The moment produced by AX about point C is also 0. I don't need to calculate the moment produced by AX. So basically, I only need to calculate the moment produced by AY and this 8 kilonewtons. That's it. And they are very easy to do, right? So in fact, we can start with the moments at point C. We can start with that one. I'm going, because this is a 2D problem, I'm going to calculate only the Z component of the moment. The other two X and Y components are 0. So let's start with the moment produced by this AY about point C, this one. That moment is going to be clockwise or anti-clockwise? Clockwise, so minus. What is the distance I need to include? This 1.5, right? Minus 1.5. And I need to multiply this distance by the force, AY, in this case, is the reaction. So the moment produced by AY is this, and now I need to add the moment produced by these 8 kilonewtons about point C. How much is it? Distance. Or is it going to be clockwise or anti-clockwise? Clockwise, so minus again. How much is the distance I need to consider? 1.5. And then I need to multiply this by 8 kilonewtons. And these are all the moments we have about point C. And in order to be in equilibrium, this needs to be equal to 0. So from this equation, you obtain AY. How much is it? It's positive or negative? Negative. How much? 8. 8 kilonewtons. Negative. What does it mean, negative? It means this AY this was our initial orientation. You agree? Okay, so I need to delete this. So we assumed our initial orientation for this AY was positive with the y-axis, but we obtained minus 8 kilonewtons. So this minus tells us that our initial orientation, in fact, is not correct. So we need to come here and reverse. So our AY is going to be a force in this direction, and this is going to be equal to 8 kilonewtons. Okay? You all agree with me? That's it. So, don't worry at the beginning when you are putting your reactions there, if it is to the right or to the left, it doesn't matter. Assume an initial orientation, and then if you get a negative, it means your initial guess was wrong, and then you go back and replace. This is done. Now the resultant of the forces. What are the x components? What do I have in the x direction for the forces? Ax. What else? Do I have anything else in the x direction? Positive or negative? Minus FCD cos of 45. What about the y direction? 8 or minus 8? Minus 8. What else? Minus 8 again? What else? Positive or negative? Negative. Minus FCD sine of 45. Very good. So this needs to be equal to 0 to be in equilibrium. So from the first equation we get, from this first equation here we get, it's better to work out the y component. From here we get FCD. How much is it? Which is the force in the strut. How much is FCD? Minus? Yeah, how much is that? Give me the final. Is positive or is negative, right? Minus 22.6 kilonewtons. Everybody got this? Yeah?
Actually, in more exact form, it should be minus 16 root 2.
Sorry, I don't understand.
As in FCD, but in exact form, minus 16 root 2. Instead of minus 22.6.
I'm not quite sure if I understand what you are asking.
As in the value of FCD,
Yeah.
in exact form.
Oh.
That would be 16 root 2, minus 16 root 2, I mean.
No, if you solve this equation, you get FCD.
He's saying if you solve it, you get 16 root 2, which is equal to 22.
Yeah. You get this result at the end. It's the same thing, right? So what you want to do, let's see if you want to, instead of using sine of 45, you want to use square root of 3 over 2. Is it?
Yeah.
You want to replace sine of 45 with this.
Basically, calculated minus 16 over sine 45.
Yeah. Yeah, it's correct. So, okay, so if we solve this, you will get what? You will get FCD is going to be equal to minus 16 over sine of 45, right?
Yes.
And this is equal to minus 22.6. Isn't it?
Well, three significant figures.
Okay, so how many decimal places you want to include? 2? Okay, give me one more decimal places, please. 3? 2? 3? This is not very important here, okay? The important thing is to get the resultant, the moments, write the equilibrium equations, represent the reactions properly. Okay, so this means what? This means our force in the strut will need to have the opposite direction. But before that, if you now replace this FCD with minus 22.63, you will get the reaction AX. Can you please tell me?
Minus 15.98.
15 point?
60.
Is 60 exactly? 16 exactly, like this, right? Very good. So also negative. So let's start with FCD. We obtain the negative force. So it means we need to reverse. We need to reverse. And then this is 22.63 kilonewtons. So it means our strut is going to be in compression. And for our reaction AX, we got minus 16. So we also need to reverse this reaction here. So it needs to go in this direction and equal to 16 kilonewtons. You all agree with me? So this is our reactions at A, at D. But in your exam, there was one more question, which was calculate the reactions at point C of the beam. And I'm going to take that question to introduce another very important thing, which is Newton's third law. And I'm going to start. So maybe I can copy this. Let me do it. Just a moment. Select, copy this. Just a little bit more before we go. This part is very important. What I'm going to say now is extremely important. Extremely important. I just need 10 more minutes of your attention, then we can go 15 minutes a little bit earlier. So the question now is, I want to know. So basically you will have the beam like this. You will have this 8 kilonewtons. And then I want to know the reactions at point C. C, Y, and CX. Point C of the beam. Alright? We know already the reactions at point A. 16 and 8. Right? I want to know this CX and CY, the reactions at point C, at the inch C on the beam. And why is this important for me? For me, no. Why is this important for you? Because we know what we know. We know the force in the strut. We know that our strut, I'm going to draw it here. Our strut, we know it will have a 26.63 force in this direction, right? Let me just move this a little bit more. Which is the same as this. This is the force in my strut. Okay? So, this is, if you want, the free body diagram of my strut only. Where I have this force of 22.63 kilonewtons in the axial direction of the strut. And this force is what? For example, this is my point C, right? This is my point C in the strut. And this is my point C in the beam. Okay? I'm going to delete these reactions here. So if we look now very carefully at point C in the strut and point C in the beam, what we have here, this force here that we have in the strut represents what? Represents the action that the beam is doing in the strut. Okay? It's like, for example, if I come to this point here, and if I push this column with the force, so in this column, in this point, it will have a force of 22.63 in the column, right? So, but if I do that, look, my hand will not move, right? It's in equilibrium. So it means what? This column is reacting to my hand with the same force in the opposite direction. You agree? So this is Newton's third law. So this means I will need to have at point C this same force of 22.63 kilonewtons, which basically is the reaction of my strut into my beam at point C. So action, reaction. We need to have, if you look at these two forces very carefully, these ones I have here in green, inside these green circles, they are the same force, but they are opposite in direction, right? Because this one in the strut is the action of the beam into the strut, and the other one in the beam is the reaction of the strut on the beam, with the same force, but in the opposite direction. And if we now look at this beam only, we know that we will have at point C of my beam, I will have this 22.63 kilonewtons. I can easily say that my horizontal reaction and vertical reaction, so this is going to be my Cx, is going to be equal to what? You tell me. So, how much is this angle? 45, right? So this Cx is going to be equal to what? Yeah, please say. 22.63 times sine 45 degrees. Very good. And what about this, this vertical component, Cy? Is going to be equal to what? 22.63 cosine 45, which is equal to sine of 45, but, right? And this answers our question. Reactions. What are the reactions of reactions at point C at the beam? And that reactions are this Cx, Cy, and we obtained that from Newton's third law, action-reaction. We knew the force in the strut. We know that same point C on the beam needs to have the same force but in the opposite direction. Okay? Yes?
So why don't we consider that 16
Yeah, at the end you will get that, right? This is going to be 16, isn't it? How much we obtained before? 16, right? This is going to be 16 kilonewtons, and this is also going to be 16 kilonewtons. You get that, isn't it?
Can you explain it with just the external forces? now?
The external forces.
Because you can just say that in the x direction you have 16 to the left, so it'll be 16. The reaction will be 16.
What external forces are you?
So you have the force of 16 kilonewtons to the left, and you've got 16 going in the vertical direction also.
These two here in black, right?
The last one in red.
Right. So the red is the reaction of the strut into the beam.
So can you, instead of using the force, can you just use the external forces to give your reactions? So you've got
Oh, this external. Oh, okay, I know what you mean. These 8 kilonewtons.
Yeah, you go there. Give me the same answer.
Well, so what you are saying is that if you isolate only the beam, so let's do it here. What you are saying is that if I isolate only the beam like this, so you will have here 8 kilonewtons at this point, right? You will have here. Oh, sorry, they are in the opposite direction, right? This is 8, I think, right? And this is 16. Is it? Yeah, you can do this. It's perfectly fine. So this is your Cx, Cy. Oh, sorry. Cy, right? And then you calculate resultant of the force is equal to 0. You need to get the same thing. And it's very easy to see. Well, we can do it here. Look. Horizontal components, we have Cx minus 16. Vertical components, we have Cy minus 8 minus 8, right? This needs to be equal to 0. So from this equation here, you get Cx equal to 16. And from this equation here, you get Cy equal to 16 as well, like we obtained before. Yeah, you can do that. But I wanted to introduce here this action-reaction, Newton's third law, which is very important to do this kind of things. And this is going to be critical in the method of joints, method of sections. We are going to talk next week. So I wanted to introduce this in this example, all right? So, any questions? No questions? So my diagram is over the page, let's say. Yeah, it's a good question. It's a good question. Just a moment. So in this example, look what I did here. I did build another free body diagram, right? Which was my beam only. So in order to isolate my beam, I had to cut my support at point A. So the reactions are there. We calculated before. And I had now to remove the strut. I had to break up that link between the strut and the beam. So that's why I'm putting now the reaction Cx, Cy. Right?